what is a random variable? So now the starting point is to think that there's some kind of abstract space omega and some sigma algebra, calligraphic f on omega, and then we have some probability measure on omega. That's the so-called the probability triple that kind of classical probability always starts with. Then we have some target space, we call it S prime. And then we have some sigma algebra there in the target space. And you could think that now omega takes the role of S and F takes the role of calligraphic S. So previously we looked at this case that S was the omega and calligraphic S is now F. Just a matter of notation, but that's how we do it. And we use omega now for this starting space. What is a random variable? A random variable is a measurable function. So it's nothing else than now f is the starting sigma algebra, s prime is the target sigma algebra. So it's a measurable function. Instead of using little f for function for random variables, we usually we use capital letters. So now x is a map from omega to s prime. And usually this s prime, quite often s prime is the real line, and then this calligraphic s prime is the Borel sets on the real line. So that's how usually the target space looks, but it could be something else. So for example, it could be the target space could also be, well, Rn, and then the Borel sigma algebra of Rn. Or in the theory of stochastic processes, it could be something, some function space, let's say the space of continuous functions on the unit interval, for example, if that's the time interval that where we look. Or if you do Bayesian analysis with, let's say, Gaussian process priors, you would have this type of space here, and then you would need to have some kind of good sigma algebra there. What you would use some Borel sigma algebra on some good topology. And this is good topology on some function space that you look at. But these topologies are part of the next course, so we don't discuss them too much here. Anyway, so we could have different things for the target space. It could be a function space if we work with stochastic processes, but for this course purposes, the target space will mostly be the real line. But we use the abstract thing, so it contains, you can think that, okay, this S prime could be something very, very complicated. For example, the so-called Cadillac functions, continue à droite, limit à gauche, the French style of right continuous left limits functions. And this could be something called J1 topology on that function space, for example. But to start things, so think about this being the real line. And now a random variable is just a measurable function. Okay. So what is special about this? Well, the thing is that yes, this is kind of flexible. So when x is mapping from here, let's see, when x is mapped from here to S prime, so that's where x is mapping. So we have lots of flexibility to define things. And let's do another key definition. So the distribution of x, it's also called sometimes the law of x, or you might denote it like this. The law of X is defined by this formula. We say Px, that's the distribution or the law of X, and we define it so that for any set, we define it to be the probability of the pre-image. And this is defined for every B in the target sigma algebra in this way. And for this one, that's the pre-image of X, and we usually use this type of notation for the pre-image. So we often say that it's the probability that X belongs to B in this way. That's the standard notation in statistics and probability. So this notation, probability that X belongs to B, is actually the probability measure of the pre-image of X. So let's do the picture again. Now, here is our omega. And now let's say that this is our real line. So if S is the real line, so assume that this our target space is the real line. So we are going to take set B here on the real line. And we are going to ask what's the probability that the value of X belongs there. So now think of X as a map from omega to the real line. And we ask then the pre-image of X is here. So the pre-image is some set here in this omega. And that's the event. So the event that the omega, the little, the kind of the element that we sample from the big omega belongs to this pre-image. And the probability measure P acts here, and it tells this probability measure P assigns a number to every event here. So what this is called is an event, and it's the event that X belongs to B. So this is the way to work with pre-images, and why the random variable is so connected here. And what is important is that we want to calculate the probability X belongs to B. Well, we would like to calculate for every set in the real line, but that's not possible for, let's say, some technicalities related to uncountable sets, so-called. There are some paradoxes that we need to rule out to make a sensible theory. But we can tell this for every measurable set here, and then we look at the pre-image. So when X is a random variable, we take a measurable set, then the pre-image is a measurable set as well here. And we can calculate the probability of that measurable set. And that's how things go. What about this distribution? So actually, this means that, okay, we just want to calculate the probability to every, let's say, Borel set in this case. So that's our fundamental mapping here. We might think that, okay, we only need to look at these numbers, and we could maybe ignore this underlying probability measure. And how this all kind of plays together is that is this. So let's do, it's called an exercise in the lecture notes, exercise 3.1. It's actually kind of little theorem. So it says that Px, this distribution of X, this itself is a probability measure. So this is a probability measure. But not anymore on omega, but here in the target space. So it's a probability measure on the target space, and in general, it could be any S prime. So S prime is the set, and calligraphic S prime is the sigma algebra there. Because this is very fundamental. Let's do a proof. I didn't leave it for homework, but let me do this homework for you. So what do we need to do? We need to calculate what's the What's this assigning to the empty set? And by definition, it was the pre-image of the empty set. This way. The pre-image of the empty set is, well, if you think about it, it's an empty set now in the omega, and probability of empty set is 0. So then that's why also this px measure of empty set is 0, and that's the first property that we need to check for something being measured. So for something being measured, the next thing we need to look is the countable additivity. And so for this, we take B1, B2, a collection of sets now in the target space and which are measurable, and let's take them to be disjoint. And we ask, okay, do disjoint unions translate into sums? Then denote A1 is the pre-image of B1, A2 to be the pre-image of B2, etc. What can we say about A1, A2, and so on? B1 was a measurable set. X is a random variable, so it's a measurable map. It means that this pre-image of B1 is a measurable thing, so that means that A1 belongs to F. It's a measurable set. A2 is a measurable set, yeah, and so on. So these pre-images are measurable sets as they should be. Are A1, A2, etc., are they disjoint or could they overlap each other? If we look again, let's see if this is the target space S prime, and there's let's say this is B1, this is B2, this is B3, and they are assume that these are disjoint, B1, B2, B3 disjoint. If you look at the pre-images here, so X minus 1 B1 is something there, mapping there. X minus 1 B2 mapping there, and X minus 1 B3 mapping there. Could these overlap? Assume that these two overlapped, so then we could, what would happen? We would find a point here, which means that it would be in both of these. So X would map this point to B1, but it would also map this point to B2. But because these are disjoint, it's a contradiction. X can only map this into one point, and they cannot be in the different sets. So that's why, because there's a contradiction, we conclude that these A1, A2, etc., they are also disjoint. Let's clean a bit, and let's conclude that these are disjoint as well. When the starting sets were disjoint, the pre-images are disjoint. And hence, we can conclude that what happens to the union of bk, k from 1 to infinity, this is now the probability of the pre-image of the union of k, bk. Then we know that this union can be taken in front as well. That's one exercise to look. And this is the probability of the union of AK. And we notice that AK are measurable and disjoint. So that's why we use the fact that P is a measure. So then we can take this as a sum of probability AK. And this is a sum from K1 to infinity Px of BK. So we actually note that for disjoint, we have countable additivity. So we conclude that Px is countably additive. As a measure should. So is there something more? Okay, let's not do this square yet. Is there something more to conclude what we wanted to say? We wanted to say that the distribution of X is a probability measure. The final thing is that for this to be a probability measure is that what's the measure of the full space? And what is the full space now? It's not omega. It is the target set S prime. And now we look, okay, the pre-image of X, the full set S prime. And we already know that the full set, the pre-image is the full set in the starting place, so it's omega. And the probability of full space, because P was a probability measure, so this is 1. And now we are done with this proof that the distribution of something is a probability measure. Okay, what have we actually done? What we have done is that we start with omega and some probability P on omega. Then we have a random variable. And we actually get another probability measure, Px, now on the real line. So somehow this original probability measure here was defined on the full omega, and this is only defined on the real line or in the target space. What you could actually think about this is kind of, you could think that this is somehow the joint distribution of everything. In statistics, you could think that, okay, this is the joint distribution of somehow everything that you could measure or observe. If you would know this, you would know, you could calculate probabilities of everything in the world in a sense. This is somehow, this you could think that it's the marginal distribution of this random variable X. That, okay, we fix our focus on X and then we look at only, okay, what are the probabilities associated to random variable X? So that marginal distribution is kind of describing what's happening there.